And so the next case study that I want to talk about is showcasing the screening abilities. So again, quantitative data is great. That's what a lot of mass spectrometry is used for, but we can also get some pretty valuable information without doing any quantitative analyses. So when it comes to contamination in manufacturing, well, when it comes to manufacturing in general, we know that establishing and standing up a line is a very costly and time-consuming process. And when we think about some of the common defects that we have to work through as we're standing up that line and increasing its efficiency, contaminants are one of those major issues that can cause either quality problems or potential safety risks. You think about shorts and potential fires that can happen in a battery cell. So it's very important to not only identify that your contaminants are there, but also to quickly diagnose where they're coming from so that you aren't having that problem systematically in your manufacturing line. And the challenge is that contamination originates from a lot of different sources, right? Anything from the raw materials to potentially coming off of the manufacturing equipment, and even just the environment and the human handling, all of those different processes that go on. And so what we did in this study was look at a traditional graphite anode that had been freshly manufactured, so it had not been assembled into a cell yet. And we sprinkled some steel particles on it just to demonstrate the Massbox's ability to test for contamination. And so you can see an image from our macro camera, where in this analytical session, we analyzed some cathodes as well as some anodes, but the sample that I'm going to talk about, particularly for this study, is that top sample, which was just cut out of a large, anode roll and again, sprinkled with those steel particles. So the way we went about screening this sample for the contaminants is we did a quick elemental map. So we scanned a millimeter by millimeter area with a 20 micron laser spot size. And this is an example of some of the maps that we got from that first scan. So first of all, let me remind you that every single one of those pixels is one of those 20 micron laser spots that has that full periodic table behind it. And each map is relative to itself. So where you see very bright colors in an individual map, those are going to be relatively high concentrations of that element. And then the dark colors are going to be relatively low concentrations. So on the carbon map, for instance, we see a lot of bright blue. We see it's fairly evenly distributed. That's exactly what we would expect for a graphite anode, to have a lot of carbon in it. And then on the chromium, we see essentially, this dark background of essentially low concentration. We wouldn't expect to see much chromium in an anode, but a few hot spots there. And so what I've also pointed out is the stainless steel powder that we used has quite a bit of iron, chromium, and nickel in it, with an average particle size of 38. And so clearly, these hot spots are likely those stainless steel powder contaminants. So we went over that area with another scan, so about a 500 by 500 micron area with a 15 micron spot size this time. So a little bit higher resolution, a little bit smaller. And sure enough, saw those same particles in the chromium map that also corresponded with hot spots in the exact same spot on the iron and nickel map. But what we also noticed was another high concentration spot on the nickel map that did not correlate with the high concentration of chromium. So again, because we have all of these elements there in the elemental maps, we could very quickly look at some other maps and see, where else are we seeing this hot spot? And interestingly, we found it across lithium, manganese, and cobalt, a bright spot with essentially, no concentration in the background behind it. And for those of you who know batteries, you're likely thinking about the lithium, nickel, manganese, cobalt cathodes. And that's exactly right. So, in this particular case, again, this was a lab study. We intentionally sprinkled stainless steel powder on this anode. And this anode had been shipped to us in the same container with an NMC cathode. So this contamination likely happened during shipping. But what this shows is that we could identify this in a manufacturing environment. So the industry knows that, especially if your cathode and anode line are close together, you may get some cross-contamination between those two different electrode sources. And this would be really important to diagnose and make sure that you're not assembling that full cell with this contamination issue on it, or you won't get the performance that you were expecting out of your battery cell. And of course, this is a battery example, but you can see how this would be valuable for any sort of contamination or any sort of material process. So again, because the Massbox doesn't have to tune for certain elements, we didn't even know we were looking for a nickel manganese cobalt cathode particle here, but we were quickly able to identify it with the scanning that we did.